I'm going to be going over some of the analysis, design, and certification challenges, actually expanding a little bit on a few of the salient trades and challenges that Mark brought up. Certainly won't be able to do them all justice. So as Mark had mentioned, distributed electric propulsion really gains all of these benefits through this tight interaction, this tight coupling between what might have traditionally been considered loosely coupled analyses. So if we're going to be able to quantify some of these different design trades, we want to make sure that we have analysis tools that can capture these interactions. One of the biggest and early contributors here is this idea of a cruise-sized wing. So briefly to describe, in wing sizing, a traditional aircraft designer is trying to choose between low speed and high speed performance. You want to cruise at high speed. That's why you got into the airplane in the first place. And so V squared is working for you, and you don't need a whole lot of wing to be able to support that aircraft. However, you want to actually be able to be somewhat safe as you approach the ground. You want to be able to land on small runways, be able to handle gusts and anything else. And so that ends up pushing you for a much larger, or that can push you towards a much larger or much more complex wing than you would initially have. So what we're trying to do with distributed electric propulsion is essentially fool the wing into thinking it's going faster. The propellers are providing an enhanced velocity over the wing, and that is what is enabling us to have a smaller wing here. Now, this comes with it a lot of baggage in terms of the analysis. So I might do my my initial conceptual design of my propulsion or my wing in some isolation and try to merge them a little bit later. Well, now I need to know that slipstream. It used to be sort of a byproduct. I wanted my propeller to be an efficient thruster, not an efficient producer of induced velocity. I need to actually capture that through the aerodynamic and other optimization of my wing. Also, this is going to do some bad things to my lift distribution. I like to have nice, smooth, elliptical lift distributions, so I have minimum induced drag. But now, between all of the swirl and everything else I'm inducing into the flow, that's going to complicate my wing design. There is a trade to be had there. How much can I augment the wing versus how much induced drag can I carry? The very fact that I have to put a bunch of these extra nacelles on this wing, so that's going to come with some drag penalties. There's going to be a trade-off there between the number of nacelles that I put on and the size and any of their cooling requirements as well with the cruise efficiency. And then actually for the design of the propeller itself, we typically design propellers for maximizing propulsive efficiency. It's why one of the reasons why helicopters have very large disk area is that you can get thrust from m dot and delta V, or some product thereof. So m dot is mass flow, goes through a very big disk area. You don't need a whole lot of delta V. In our particular case, we want a whole lot of delta V, and in some cases, we don't want a lot of thrust to go along with this. Thrust is great for takeoff. Thrust is great for climb out and cruise. It's not so good on approach. If I want to be able to approach at fairly slow velocities, which is one of the reasons why I'm bringing down this wing size and blowing the wing in the first place, I don't want to have a whole lot of thrust, or else I'm going to accelerate out of that. This is actually one of the reasons why you see a lot of these designs. We're not talking about 4 or 6 propellers along the wing. You see there's 18 and 20. There's a fundamental trade here between disk area, which is going with d squared, and the disk diameter, which is really showing how much of the wing that you're blowing. So those are some of the interactions that we need to quantify early in this cycle, and we've been developing some tools to be able to capture that. And actually, if I could speak briefly on the design tools themselves, we work across a variety of orders. We don't want to necessarily always go for the highest order design tool. Sometimes, as we're trying to just even quantify what these trades are, we just need something that's fast and shows me some relative differences so I can understand some trends. And maybe I can do some spot checks with higher order tools. And as I start to zoom in on a particular attractive region of the design space, actually spend some more time on some higher order methods. We mentioned this is very cross-disciplinary. Actually, it's been a lot of fun this past year working with the acoustics folks. In my former life, I used to do a lot of system reliability analysis, and so I was usually stuck at the end of a design cycle, and so then I had to tell somebody their baby was ugly. So being in getting them involved early here, I think we can make a lot of very good design decisions that certainly affect the performance of the aircraft. We have these boat propeller looking things because they really want us to slow down that propeller tip speed. It's a giant source of noise. Casey will discuss this quite a bit later, as well as some of the very interesting trades that can happen by varying the propeller RPM. So by, when you have 1 or 2 or 4 propellers, synchronous is probably good, so you don't get a lot of those variations in the sound quality. But when you have 18 and 20, you have a lot of degrees of freedom that are available to you. Related to the design challenges, so, analysis, design, certification, they all sort of go hand in hand, but one of the highlights, one of the issues that I'm looking at now is what are the V speeds? What are the speeds I'm going to use for takeoff, landing, and approach? So in the traditional design paradigm, an approach speed is related 23 to 30% of your power off stall speed. Well, my power off stall speed is 50% higher than my power on stall speed. So, are these propellers, or are they propulsors, or are they high lift devices? Some very interesting questions to be answered there. A lot of these other approach speeds have to do with off-nominal conditions, gusts, engine failures. That's what sets a lot of the decision speeds for takeoff. So I think there's a great opportunity here to integrate, risk analysis, hazard analysis, probabilistic analysis, to be able to really understand what are going to be those long pulls in the tent, what should our new design airspeeds be. Related to that, we talk about off-nominal conditions being a driver for some of these speeds. Just think about the human interface here. We're talking about a pretty significant change from the current paradigm, where the human operator is the failure detection, isolation, and reconfiguration mechanism. So I show here there's a B-52 pilot with a fistful of 8 throttles on approach, and that pilot is the one that's going to have to determine how to adjust those in the event of a failure or anything else. Imagine now having 20 throttles in front of you. In fact, the current rules say you have to have a single power level for every single propulsor. It's not going to work. Can you imagine an engine failure? 1, 2, 3, 4, 5. 1, 2, 3. That's the throttle. Yeah, I got it. It just simply will not be possible. And what's a big change here is a move from automation to actually putting some decision authority into the hands of the machine that used to be with the pilot. That's starting to sound a little bit like autonomy. There's certainly a lot of work gone into single pilot operations, into the haptic controls work, that instead of just saying that autonomy is going to enter aviation through UAS, which certainly there are some compelling cases there, I think that there's a role here for some shared responsibilities between the operator, pilot, and the machine. We talk a lot about certification, and sometimes it's a bit of a dirty word. In fact, analysis and design and test are all things that we see as ways to enable technology development, and certification is often seen as a barrier to it. In fact, there's the saying that regulations or rules are written in blood, and that's usually due to bad experience with current or old technology. And in fact, say targeting, say commercial operations, you have a very high standard to achieve. When the person sitting on board the airplane does not have operational authority, when they are just meat in the seat essentially, we have a very high standard that we apply to that. There's a different level of risk tolerance. We're talking about 1 per billion flight hours. However, there are more risk-aware markets, like in the case of general aviation, that have a slightly lower barrier of entry. Not that 1 per million flight hours is significantly lower, but a slightly lower barrier to entry. There are no test programs in the world that can generate this brute force statistical data for new technologies. That doesn't mean that there aren't opportunities to leverage simulation-based or hybrid approaches. I'm thinking of participated in some of the LD-CAP experiments that were done here just a few years ago, where was merging simulation and flight test, looking in that particular case for sense and avoid. But otherwise, this idea of spiral development and targeting these early adopter markets is key. One example I think that is very relevant here is the light sport aircraft rule. This was created in the early 2000s, and this basically said, the FAA said, we're going to try something new. We're going to try to lower the certification standard for, or the barrier to entry for very light aircraft, as well as to pilots. So they changed the rules for the operators as well as the rules for certification. And in fact, there's actually a difference between rules and standards, which are often seen as the means of compliance to the rules. And what the FAA did here is they divorced the two. They said, we're going to be responsible for the rules. We'll set the rules. We'll try to make them as technology agnostic as possible. And we're going to let now an industry, or not just industry, but an overall consensus standard making approach. They used ASTM in this particular case. We often use the term industry consensus, but actually they can't have more than 50% of industry members to kind of keep them from polluting the pot too much. So this consensus standard approach to rulemaking allows for faster adoption of technology. I think I heard that a notice of proposed rulemaking through the government takes 7 years, and usually a change through a consensus standard takes about a year. So at least if it's backed up with the appropriate level of data. And what's very interesting is right now, because of the success of this in this early adopter market, the FAA has moved on to the next level. So they are now rewriting Part 23. The light aircraft certification standards go up to most aircraft up to 12,500 and commuter category aircraft up to 19,000 pounds. And they are doing the same thing. They are taking a 300-page rule and embedded means of compliance, and the draft rule, which the NPRM is imminent for, is about 30 pages long. And in Rev 1, ASTM has just pulled over all of those existing means of compliance, and they've tried to clean it up a little bit and get rid of some of the redundancies. And now this committee, F44, has responsibility for maintaining that standard, maintaining those means of compliance. And so this, through membership on this committee, I am a member, but that it is certainly not limited to me. This is really a great opportunity to be able to start bringing in some of these new technologies so we can bootstrap the effect of these early adopters and really build up this data as we start to target larger and larger audiences. And that's how I would like to finish this up a little bit I think successful technology adoption here is not just about technology development, but thinking about this transition and gathering that data, thinking about that last piece. Often I hear the technology readiness level scale, TRL, used to describe the maturity of a technology. If you're not familiar, probably are, but why not? 1 is, basic napkin sketch, and 9 is reduced to practice. And you often hear folks will say, well, the secret to technology adoption is to bridge the valley of death between TRL 4 and 6 or so, which is kind of from lab test to basically first real type flight tests. But the interesting thing is that TRL 9 for a launch vehicle implies a very different level of risk than TRL 9 for a commercial aircraft. So I think it's very important here to address this adoption path, and perhaps maybe it's not just we're going to go into ODM tomorrow, but let's see about getting distributed electric propulsion into piloted GA-type aircraft first. It might be about getting autonomy into UAS, or getting some sort of shared decision authority, might be for IFR operations type first before saying we're going to give the computer all the keys to the decisions on this aircraft. So I think with that, that's about all I have to say, and happy to take questions at the end. So thank you.